Can you hear me? Is it fine? Okay. Yes. So what I'm going to be talking in this talk about is one particular vulnerability of federated learning, which is actually the aggregation step. So let me just go into that. But before that, let me just acknowledge my wonderful collaborators, and in particular, I would like to highlight Eduard Gorbanov, who is currently a research scientist in our lab, and he's one of the main developers of many of the works that I will be presenting here, especially regarding the robustness. So, all right. So let me start with the motivation and why federated learning is very important. So first, traditionally, we would implement intelligence by collecting all the data to one location, and then we would just train the model. So with the increase in our available compute and training data, we move from a very centralized location to cloud-based solution, and we can attribute much of the machine learning success to two main things: is large-scale training infrastructures and the fact that we have vast amounts of training data. However, we have to realize that where those data come from. So commonly, they are collected from the users, and user might have some negative privacy implications when we do that data collection. Also, there are several privacy initiatives, such as GDPR in the European Union, that actually kind of limit the access towards those data. So therefore, what we might be losing, if we are not kind of obedient towards these privacy regulations, we might be losing access to the second pillar of machine learning success, which is having access to the vast amount of data. So this is actually where federated learning kind of comes into play, and then the main proposal is, okay, like if we cannot really collect the data, then let's just bring training to those devices, and we will do all our training within the devices, and we will therefore we will obey this data locality paradigm, meaning that everything that we do about the data is done on those devices where they were collected. Okay, so there are two main settings. One is cross-silo federated learning, where what we have is we have several institutions, maybe a small number of them, that they would like to collaborate. For instance, we have a couple of the hospitals that want to train, can have an AI doctor, but the thing is that they cannot just pool all the data together, because these are private health records that they cannot just directly share. And then there is a second setup, which is cross-device federated learning that Peter was talking about. All right. So with this, I think in a nutshell, the federated learning training loop can be regarded as this one. So what you're going to do until you get a good model. So I have at the server, I have some estimate of the model. I send that to all my available clients, or a subset of them. Each of them, I ask them to compute in some way their local update, that then communicated back to the server, and then server just performs the simple averaging to get the new model that I'm going to work with. But clearly, this has very naive, or very, this point will actually be a single point of the failure, and the reason for that is federated learning as such, because I have clients that might not have a mutual trust. They would be a very easy target for attacks. Because what might happen is that some of those clients that operate on their local data, there might be either malfunctioning or they might be even malicious, and we refer to those workers as Byzantines. So those are the ones that might send an incorrect information. So if these are malicious, the common attacks that we want to perform, let's say we can perform to the system, we can just flip the sign of the update that we should be communicating back. Or when we do actually training, in order to essentially make training not work properly, we just flip all our local labels that we have for our data, or just I can send a random direction. But what I can actually do, I can actually send anything, and then I could possibly just destroy all my training efforts just due to the fact that on the server I perform averaging. Now, of course, if we know that this is a single point of failure, the question is how we can actually make federated learning more robust and be able to defend toward this against this very simple attack. So the main idea is to consider what we so-called Byzantine robustness. So originally, what is the objective that we're trying to minimize is just, so X is here, is the solution that you're trying to obtain, and F is your global loss, and Fi, that's just the average of local losses on those clients that perform the training. So clearly, if we have potentially malicious clients, what you're trying to do, you should be ignoring their updates. So actually, your true objective that you should be optimized is just perform the average. Your loss should be average only over the good workers. Then Byzantine workers we will denote as B, and it should be the case that their union are all the clients that we have, and there should be zero intersection. So client cannot be at the same time both good worker and Byzantine, okay? And then the question is, since this is not a parameter that we know, it's something is how to defend against some attacks. It's actually how to differentiate. The problem just switches into how to differentiate between these two, which ones are the good ones and which one are the Byzantine ones. So what's the setup? So in order to actually be able to argue, like when can we defend and what are the limitations, we have to define a certain setup. So what our setup is that Byzantine workers, they're omniscient, so they know everything about the problem, even the defense that we are using. And this is in order to provide the strongest guarantees possible. So if we can provide guarantees in this particular setup, that applies everywhere. And also, what we're going to assume that the fraction of Byzantine is less than 50% of all your workers, because otherwise it just doesn't make sense because they can choose what problem like kind of you're optimizing, and you have no way to distinguish between that. For the good workers, we also have to make a certain assumption, and that assumption, what we're going to assume here is that their loss function cannot be arbitrary heterogeneous. And the reason for that is if you allow arbitrary heterogeneity, then there is no way how you can distinguish between a good update and Byzantine update, because you can always argue that the Byzantine update is just due to the local heterogeneity of the data. So that's why we have to have some assumption about how these things, what kind of data heterogeneity we have. And usually, since we used commonly gradient-based optimizers, we assume that the gradient, so gradient with respect to data of the local client, when we link it to the gradient of, like the true gradient as an average across the all good clients, is actually bounded. Bounded by a certain quantity, and you can here notice that if this is 0, that means that actually all the clients, they optimize exactly the same loss. Okay, and then what's going to be the other goal is that we would be able to aggregate only good workers, or we would limit the effect of Byzantines that they can have on the averaging. And how are we going to achieve that? So the common approach in the literature is to just replace the averaging with some kind of more robust aggregation rule. And in the next slide, I will try to answer like, how to actually choose such aggregator. So what's the common approach is to use so-called middle seeker aggregators. So I have a definition here of a few. So what might be looking at, so we are looking at the aggregators that are able to filtrate out the outliers. So one possibility is instead of looking at the mean, I would look at the geometric median. That's essentially very computationally heavy to get the true value. So in order to simplify that, I can also look at the element-wise or coordinate-wise median, or so-called crumb estimator, which works as a simple mean, but it actually ignores a certain number of the outliers. Now with that, so this is something, these are the aggregators that were proposed in the literature, and the question that we can ask is, are these actually really a robust aggregator? So what we mean by that, so a standard definition of what we mean by robust aggregator is that if the updates, so here GI and GJ are the updates that are sent by the clients. So if these are in expectation somehow close together, it should be the case that G hat, here that's output of my robust aggregator, it should be close to the true mean over a good workers. And how close is it? So it scales with the fraction of Byzantines, it scales with what I have as a notion of variance across the updates and some constant that's constant that depends on what type of aggregator I'm using. Now, in having these, you can actually ask, okay, are these actually robust aggregators? It actually turns out not. that we can actually hack those aggregators. But thankfully, as proposed by Karimi Reddy in 2022, you can actually make them robust if you include the extra trick that's called bucketing. And what it does, essentially, it performs a partial averaging before performing the robust aggregation. Okay, so having this, these are essentially, some essential tools that we have to employ in order to make our optimization or our training in federated learning more robust towards these potentially malicious or malfunctioning clients. Now the question is here, like, even with this setup, the Byzantines actually can be very powerful. And important thing here is to look at what actually makes them so powerful. So what makes them so powerful is that if you have a lot of noise in your system, so here, how do we actually define the noise? So if this is a distribution, so the blue dots are distribution of our good updates, what might happen is that if Byzantines know everything about the problem, they can actually concentrate their updates towards the edge of this distribution, and then you can naturally see that none of the actually robust aggregators would be able to filtrate them out. And what they are able to do, they are able to shift our solution towards the direction that they want to shift it to, and we won't be able to essentially defend very efficiently against those. So once we have a large variance, Byzantines can easily hide, and it will be hard to detect them as outliers because there is actually large space in which they can hide. So very natural idea that we can do. Okay, so can we make this variance actually significantly smaller? Because if we can achieve that, then simply the Byzantines then don't have that much space to hide. So there will be very limited amounts of very limited direction in which they can actually shift our updates, and therefore they can only kind of have a very limited power when it comes to destroying our model performance or having effect to the whole model training. All right. So now the question is whether that's actually achievable. It turns out yes, you can do it. And the technique that we can use is so-called variance reduction that works in the following way. So we have some, so for each of the update that we do locally, we have a certain estimator that is stochastic because we usually work with a very large amount of data, so we cannot compute precise updates, but we can have some good estimator of those. And what variance reduction does, it actually slightly changes those estimators such that in expectation we do roughly the same thing, so either the same thing or roughly the same thing, but the variance actually shrinks significantly. So there was a prior work on this that uses so-called Saga estimator to construct this local update and improve the Byzantine robustness. But it actually turns out that even though that's like a very natural idea, their work actually does not have much of improvement in terms of both theoretical properties and also practical performance. And the reason for that is because what we show is essentially the Saga estimator. So the estimator that they use to get variance reduction is very sensitive to unbiasedness. But what we saw before is actually none of those robust aggregator that I showed you is biased, and therefore these two things just are not compatible together. So there was still a gap in the literature that we addressed here within this work, where we show that you can actually use a much better estimator that's already biased, and we show that this update is compatible with this biased robust aggregator, and we get both theoretical state-of-the-art rates and also very good practical performance. So on top of that, another important challenge to consider is partial participation. So Peter was talking about cross-device federated learning, where you might have thousands or millions of clients. So what might be the case is, in order to actually run federated learning algorithms in this challenging setup, what you actually have to do, you have to sample your clients in a way such that you would make everything computational scalable, and also, I mean, those clients are not available at every single time. But what a partial participation and Byzantine robustness, why they don't actually play very well together, is what might happen is that with a small probability, but what might happen is that the majority of your sampled clients might be Byzantines. And therefore, if majority of their sample clients are Byzantines, there's essentially no robust aggregator can save you, because those ones, the Byzantines, they are the ones that choose what is the mean, so they can shift your current solution arbitrarily. So the question that we ask within this study is, in this very challenging scenario, can we still make it Byzantine robust? And it turns out yes. And there is one particular trick or technique that you have to employ in order to make this a Byzantine robust. And how you do it is that, okay, so first we have to assume, so the assumption that we have to have is we don't need to have, in every single round, we don't need to have majority of a good clients, but what we need is that this holds at least with probability 1/2, which is natural because at least in half of the rounds, we have to be able to move towards a good solution. And what we show then, like if you have this plus what you do, you actually limit the power of each update by clipping, then you can actually make this setup Byzantine robust. So maybe linking this back with the Peter's talk, it's also like a similar thing that you have to do in differential privacy. In order to dare to actually preserve privacy, you also need to have that each update has some kind of limited power, so you can still argue about privacy. So how that's achieved, it's through this clipping operator that's defined over vector x and some scalar lambda. And what you do is, if the norm of the vector x is less or equal than lambda, you do nothing, so you just return x. If this is greater than lambda, what you do, you just apply a scaling such that the norm of this vector would be exactly lambda. It has very nice properties. That means that our update would be always bounded in norms by the lambda. Also, we can control the bias between what we intended to send versus what we have after the clipping. And also, because we just apply scalar transformation, we also preserve the direction. So therefore, that's nice that you can still argue about convergence properties, and this thing also works in practice. And what you would see that if I were not to apply clipping, I'm actually not able to learn anything, while if I just apply the clipping and use exactly the same algorithm, I suddenly just get back all the properties that I would get with the full participation. All right, so up to this point, we're talking about how to make algorithmically, given already the problem that we are optimizing, how to make optimizational learning within this challenging setup working as efficiently as possible. But there is a certain fundamental limit within Byzantine robustness. We cannot push through only using algorithmic developments. And the reason for that is, if actually this is result is due to Karimi Reddy. So what they show that if there is a heterogeneity in terms of your data, then you cannot do better. So you cannot hear your gradient. So in the optimal, what we usually have that the gradient is 0, that your gradient cannot be small. So you can only guarantee that you would minimize it up to this neighborhood, that the neighborhood scales with the number of Byzantines and the heterogeneity in data. And this is algorithm independent lower bound. So there is no hope that you would improve this just by designing the better algorithm. Then the question here is that actually, given this, can we do better? And can we somehow remove or reduce this effect of the curse of heterogeneity? It turns out that you can do it, and there are two techniques. At least the first one was a very surprising result to me that we got, that you can actually do it through the personalization, or you can do it if you have at the server, you have availability of the extra data that very well represent the problem that you're trying to solve. So how to break this curse of heterogeneity in terms of personalization. So first, let me define what I mean by personalization. So standard way how we employ personalization. So what we had before, this was our standard objective, where we're just trying to find a single X, so single model X that works well across all of the clients. But in many cases, this might be actually quite restrictive if we're only looking to find a global model. And the reason for that is there might be not really a good solution that works for every single client. Natural example of that is, okay, if I have the next word prediction, that very much what should be the next word depends on who is the speaker. Or also, in many cases, you want to have personalized medicine and so on and so forth. So therefore, like you should be, what you can try to do is actually look at the personalized objective. And the difference there is I'm not only trying to find a good global model X, but what I'm trying to do, I'm having some kind of a private part, W1 up to Wn. So that's specific per every single client. You can think about that as some kind of adaptation to the local data. Okay. So then, with that, there's a question like how to do the personalization. I think the answer is actually it very much depends on what's the heterogeneity in the data that you have. I think the common approach is okay, if there is more of a feature shift in your data, then it would be better to personalize the input layer because those require a slightly different preprocessing step. You might have a label shift, that means your classification layer should be adapted, or what tends to work very well in practice, like if you actually don't understand very well what's the type of heterogeneities that you have, you can employ a small adapter to each of the layer to still be able to learn something global, but give enough freedom to each client to personalize their local solution. And for instance, for that personalization, you can use the LoRa adapters as introduced by Pranit. All right, so having this, what we show in the paper is that there is actually a particular phenomena that we call overpersonalization. So what overpersonalization means is the following. So if this is our personalized objective, we show that there is actually, so if with the right personalization, so if I employ enough personalization, then I can always achieve a zero of loss. And what we also show that this is not only our assumption, but what you can say that what you can prove that for sufficiently large models, this actually always exists. So it's rather a property than something that you need to assume. And if you know, for instance, what overparameterization is for deep learning, so this is the alternative of that. Overpersonalization is alternative of that for federated learning. And if you have all of this, the good thing is that you don't need to think about very fancy algorithms to actually optimize this. All you have to do is the following thing. So here, what I'm showing on the left is just the algorithm that can actually solve this problem if you have overpersonalization. So what that algorithm is just Fed averaging running on the X, and locally what you do, you just show that I can personalize enough. If I achieve that, I will always converge to the precise solution. So, and if you want to adapt this, so originally we did not develop this particular algorithm for Byzantine robustness, but what's a very nice property here, if you want to achieve Byzantine robustness, you just replace the averaging with the robust aggregator, and what you can show that then everything works exactly as I was describing it, as if you would have no heterogeneity at all within your system. So this was the first way how to get Byzantine robustness almost for free, if you know. But of course, there's a key limitation that we do not address in this work, and I think it's a very important open problem, is actually how do you select that particular personalization that can remove that data heterogeneity effect. Because for us, well, our proofs are not constructive, they are more that there exists personalization that would just give you that property. Okay, and then the second result is how to get Byzantine robustness by having access to some extra data. So what we have here is exactly the same setup as we had before, with the difference is that I'm going to assume that I have an extra access to, I'm going to have extra data on the server that I assume are actually are sample from the true distribution over which I try to optimize my objective. So if that's the case, I actually do optimize a slightly different objective. So I optimize only over that particular distribution, over which to which server has access, but only to some small sample that can actually just tell me like how much useful are the data that I'm getting from the client on which I'm running federated learning. So what is the key difference in compared to standard federated learning, and what is the extra property that buys us Byzantine robustness is that we have those extra data and good data on the server. So if you have this, what you can do then, if the updates that I receive, these GIs that I receive from each of the clients, what I can do then, having access to the extra data, I can actually rank them and optimize. So this guy here is, what I do here is I just tune my weights for each of the update from the client that minimizes actually my true loss that I'm trying to optimize. What you can do, this way you can actually see that if your update is not, if I can actually solve this argmin, if my update is actually not beneficial to my true loss, I'll just ignore it. The weights you would get there would be 0. This is because I'm optimizing over the simplex. And then it's actually you don't need at all the robust aggregator. Then you just use this weighted sum of the updates as your update, and then you just update your solution. What also turns out that is actually, I can actually efficiently solve this argmin. I can solve it with the solver that's able to respect all standard federated learning constraints, and that particular solver that we use here is zero-order mirror descent, which is due to Ducci et al. 2015. And here the key advantage is they can really tolerate any number of Byzantines. So the nice thing is even if all the clients, what happens is, even if all the clients are actually Byzantines trying to destroy your performance, the simple trick that you can do, I'll just add an extra update that is just 0. And if I'm able to solve this argmin, it will just tell me, like, take way 1 of that update 0, and I'm not going to shift anywhere. So I won't be able to learn because none of the clients has a good data, but if there is only one client that has a good data, I will be able to learn. And none of the Byzantines can actually change. None of the actually Byzantine have any power over destroying the performance of the model. But here, the main thing is, what it requires to have access to a representative sample of my true distribution on the server. All right, so with that, let me just conclude. So I think there are 5 key takeaways from this talk. So first, I hope I persuaded you that Byzantine robustness is an important, challenging problem if we want to deploy our federated learning algorithms. Also, what we've seen that variance reduction is essential in making federated learning more robust towards Byzantine workers because it gives them less space to hide. Also, update clipping can not only help us, as we saw, with privacy, but also can help us to scale our solution to work with partial participation. There's another important building block of scaling federated learning to work with large number of clients. And although what is very good property of this one, that even though it still works, even though in some rounds you can only see the Byzantine workers. Then what we saw that over-personalization can help you to remove the effect of heterogeneity, and that what we saw, that this effect of heterogeneity in standard setup can prevent us from converging to the optimal solution. And then the last thing that we have seen is that if I have access to the extra data, then I will make Byzantine powerless. With that, I would also like to advertise a poster presentation of the PhD students that we work together. So Abdullah will tell you more about personalization and beyond. Nurbek's going to talk about fairness and encryption-friendly algorithms. And Nico will tell you how to combine federated learning and reinforcement learning to get more efficiency from the energy grids. And with that, I would like to conclude and happy to take any questions. Yes.
In the case of our personalization, what you want to achieve with this local gradient descent training is basically our personalization means you have like a part of the model that belongs to the client, and you want to just reduce the loss completely about that one. It's like
yes. I mean, the main thing here. Main thing that actually helps you to remove the effect of heterogeneity is like through the personalization. What you can make sure is that once you find the optimal, your actual loss is exactly zero. So as I was saying, I mean, that's the same thing. I mean, that's why we also, that's why, for instance, here, so the parallel here is the following. So for what we do for deep learning models, right, like you tend to have more and more data. So in order to account for that, what you do, you're increasing your size of the model. You increasing your size of the model not because it's actually the model doesn't have like enough capacity in terms of training, but you include those like extra parameters such that you can actually optimize loss to zero. Because then if you can optimize loss to zero, there is a lot of work on that it actually helps with the convergence speed, and there is no that many things that you actually have to tune. So that's why what you see, I think, with like a scaling loss of LLMs is like the only two things that you should care about is how many parameters you have and that you have access to enough data. And then it should just keep improving. You don't need to kind of tweak the optimizer or things like that.